Yo everyone, and we're back to this episode, and this time we're going to talk about the fourth dimension. So just in case, wait, Roses?
Hi, Kappa.
What?
Roses disappeared.
Roses not
Oh.
coming?
Hi. No.
No? Oh, okay. So here we have D, we have Kappa over here, and Roses is over there, but no idea why. So just in case, quick question though. So when you heard the word fourth dimension, what did you think about? Like, how will you feel it? Like, what do you know about it?
Mr. Sharp Razor, sir, the first thing I thought about was fourth diameter, because I didn't know what the D meant.
What about you,
Fourth?
Kappa? The fourth
Like-
dimension.
Something bigger than 3D, I'd assume.
To some extent, yes. And that's actually what we're going to talk about today. So, in this case, in video editing, I will chop this whole video up into these many sections. Typically somewhere around maybe 6 or 7, I don't know, we'll see. So, first thing first, let's just make sure what is a dimension. So in this case, under normal circumstances, a dimension typically saying it's just a number just to describe some kind of state. So for example, if you want to like describe position, right? Let's say you just only use one number. So you can go
Sliders.
0 to 1 or whatsoever, and then you just use one number to describe position. And then you can also attach a new dimension, let's say time dimension. So with this, now you have two numbers. One, you can explain or describe your position, and another one will be something like, at what time, where are you? So far that makes sense, right? No?
7:10 p.m.
Yeah.
That also works. So for example, 7:10 p.m. and then you have your coordinates, x, y, z coordinates. Now that's 4 dimensions, right?
Yeah.
X, y, and z, and t. So with all these 4 numbers, you can describe at what time where something is. That makes sense. I hope.
Pref?
Alright, yeah.
That also works. That also works. Heck, if you open up Unity and then you start animating, you have that timeline down at the bottom. Yeah, that's the time dimension. And then afterwards, you select a single object. In the inspector, you can change X, Y, Z, and all that stuff. And then you can see how things move or where things are in this case. So there's this like one time I watched a video and it also says something like, technically speaking, if anything can be described by using numbers, then it can be a dimension. So what he says is, you can even include mass as a dimension as well. You can even include charge as a dimension as well. So in this case, it's really general in this case. But however, in this video, we are going to like focus on just spatial dimension, not time, not mass, just spatial dimension. Left, right, up, down, front, back. So we have that. So when it comes to like spatial dimensions, how is a direction defined as a dimension? So for example, okay, let's just say in a spatial dimension sense, how will you define a dimension?
With coordinates.
With coordinates. Okay, what about you, Kappa? How will you define what is a dimension in terms of space?
Sides.
Right? Okay. So in this case, what we can do is let's just pick a simple random direction, right? So this direction will then become our axis. anything that can be described by using this axis is a dimension. Now, if you want to introduce a new dimension to it, then that new direction needs to be perpendicular to this original axis we have, right? So for example, imagine you just start from a single line. This single line is just one direction, right? And then
Yes.
so if you want to introduce a new dimension, this new direction needs to be perpendicular with this line, right?
Like this?
Yep. So in this case, if you push the line perpendicular to itself, you will get a square. And then you go from 1D to 2D, right?
Okay.
So new
2D
question would be
2D is
something like,
flat.
to us
It's
it's
one-
flat. To us it's flat. We'll get there. So for
Who
example,
else?
so
The aliens? Like
we will get there, but not
Okay.
aliens. We'll get there. So
aliens real.
So now you have a 2D flat square whatsoever. If you want to introduce a new dimension, what would that direction be?
If it's just forward, and
backwards.
I'd
it's
assume left to
like-
right.
Yeah. It's on one plane.
So
yeah.
so your square is already forward and backwards and left and right already. If I want you
X and
to
Z.
X and Z is what we already have, right?
Uh-huh.
So if you want to add a new dimension, what that direction should be?
I'd assume Y.
Yep. Because
Ah.
what
He
you
said
got? What
why.
you got?
I was just. Oh, he said why. I was just. Did I not
Okay,
get
so
something?
here's the thing. Because Kappa did said the new dimension should be the Y direction. Like if you use Unity, we all
Oh, the
know
Y
left and
direction.
right. Yes. So in Unity, we know that left right is X, forward and backwards is Z, and then up and down is Y. Because in this case, originally we only have Z and X. And then Y, this direction, is perpendicular to X and perpendicular to Z as well. Oh wait, I think I can go grab something. I'll be right back. So in this case, here we have a Unity gizmo. We have X. Yes.
Uh-huh.
So here we have our X-axis,
Uh-huh.
left and right. Here we have our Y-axis, up and down. And then here we have our Z-axis. So originally, we only have our X-axis, which is just one-dimensional, right? And then if you want to, oh no.
You stabbed me with the
And
laser.
then if you want to introduce the new dimension, which is this one, as you can see, Z is perpendicular to X. So this direction counts as a dimension. If I were to just simply put my arm over here, and then you can see, hey, my arm is not perpendicular with X, it's not perpendicular with Z. So my arm is not a new dimension. That cannot be counted. So when we want to introduce a new dimension, which is Y over here, Y is perpendicular to X, Y is also perpendicular to Z. So Y is a valid dimension. So we have that. Choop. Choop. There we go. E. So we can put this thing back over here.
And I noticed earlier you
Yeah.
were talking about T. Is that another axis or is that a?
So in this case, we will be focusing on spatial dimensions. We will not be talking about time dimension.
No time.
Oh, time is
Yeah.
completely different.
Sort of, yep. Alright, so whenever like people talks about 4D stuff or whatsoever, they'll definitely say, alright, let's make a 4D cube. Have you ever heard of that before?
Not entirely, no.
No? What about you, Steve?
No, never heard of it.
No? Okay, so let's just start completely simple, right? Let's just start with a dot, right? Boop. Just a simple dot in space. So far we don't know how many dimensions is that, but we all know that a single dot is just 0 dimensions. It has no direction at all, right?
Okay.
So this means you can just take this point and then you extend it in any direction, right? Now you have a one-dimensional line, right? And then you take this line and then you push it, swipe it, or extract it in a direction. And then this direction is perpendicular to itself, right?
Okay.
So now you have a square. Now you take this
Right.
square, you push it in a new direction. This new direction is perpendicular to itself. And then now you get a cube, right?
Yeah. So you pick it up and it's like,
Okay?
Yeah.
That's our normal cube. Just like those cute plushies over there as well.
The
Right.
cats.
Yeah. So now here's where things starts to become interesting. So you take this cube and then you push it in a new direction such that this direction is perpendicular to itself.
wait, what?
Not left right, not down, not front back. This new direction is all perpendicular to all these three axes.
You get what, a rectangle?
No, you don't get a rectangle. No, you don't. So in this case, do you see that cube right there? The yellow cube.
This one?
Yep, this
Oh.
one. Yep. So, yep, we need that one. Yep. So, this one over here. Okay. So you can see
Within a cube.
this. So this model over here, we have a small cube in the middle, and then we have a big cube at the outside, right? So here's the thing. This thing over here is a tesseract, or in this case, a 4D cube, which is the thing. Now, here's the twist. This is not exactly a perfect 4D cube, because in order to fully see the whole thing, you need to be at least the same dimension as that thing is, or a higher dimension as that thing is. So for example, if we for example, you still remember the cube, right?
Yes.
The cube is a three-dimensional object, right? Because, you know, X, Y, and Z, 3 dimensions. We are 3D living beings, right?
Yes.
So we get to witness and feel what does a cube looks like and feels like, right? We know it has 12 edges, 8 corners, and 6 faces, right?
Feel a cube. Oh yeah.
Yep. So here's a problem. Let's say there is some kind of creature that lives in a two-dimensional world, right? In his sense or in his experience, there's only 2 dimensions. He don't know what the third dimension is, so he cannot exactly fully see a normal 3D cube, right?
Yeah.
Like
He's
for
seeing
that
square.
creature, yes, for that creature, looking at a square is like us looking at a 3D cube. So just in case, with this, since we cannot see a 4D cube, then we have to do some tricks. Like for example, what we have to do over here.
Yes.
Alright, so just in
I
case,
have-
if you still remember back in your maybe like school days or whatsoever, right? And then the art teacher said something like, or the math teacher said something like, okay, try to draw a cube on a piece of paper or on your homework whatsoever, right? How would you draw that?
Well, I draw a square first,
Mm-hmm.
and then
And
like
then?
branch, draw another square,
Mm-hmm.
right? And then connect the
Mhm.
corners.
Yep, there.
I would do
Oh,
origami.
So that is one way.
I would do origami. I would fold paper. I'd stand up and be like, guys, coach was right. We can't win this unless we try really hard.
So Steve, if someone asks you to draw a cube on a piece of paper, how will you draw it? Because Kappa did say the two square and then connect the corners thingy. What is your approach?
So from your point of view, camera, it would look like this. Like that. I
So-
would
so
draw
you're
a line
doing
like this, and it would be a flat 3D looking illusion.
Hmm. So as you can see,
Checkmate,
what the
Mom.
both of you have done is a perfect example of what we call projection. So projection is like you're trying to squash a higher dimensional object onto a lower dimensional environment. So in this case, we originally start with a cube, and then as you can see, it has left, right, up, down, and front and back as well. But in order to squish this thing onto the floor, you will need to like sacrifice a dimension, and then everything will become flat on that thing, right?
Yeah.
I suppose that's a reply.
Yes, definitely.
Okay,
Sorry, my
so
mic didn't
so
pick
just
up.
in case. Oh, so just in case, at your point, Kappa, when you draw the two squares and then you connect those two squares with four lines, right? Is every side perpendicular anymore on that piece of paper?
Every corner or edges would be
But what about the
perpendicular,
connected
hitting each
lines?
axis. They'd have a Y, X, and Z, I guess, but on a different plane. It'd look weird.
So as you can see, like when you draw it on the paper, you can find that there are several lines or two lines that they are not perpendicular anymore, right? So that is a penalty of projection, right?
Which lines, though?
So for example, you draw, okay, so for example, let's say you draw this square at the front first, right?
The face.
And then
yes.
you draw the square at the back a little bit offset, right? And then you connected the four lines, which is this one, this one, and then that one, right?
Uh-huh.
Okay, so these four connected lines is not perpendicular to the square anymore on your paper.
Oh.
Right.
Oh, yes, I see, okay.
So that's the penalty of it. That's the penalty of projection. Yes, a 2D ant on your paper can now see the whole cube, but are they perpendicular anymore? Sadly, no. It's almost the same situation. If you still remember that tesseract we have over there. Wait, where's the tesseract?
Behind you.
Over there.
Oh, can you help me take that? Ah. Okay, I think. Look, let me get out of this cube first.
I'll be the cube again.
So
Oh.
here's the thing. So here's the
My
thing.
ass is sticking out of the cube.
Oh no.
Sorry.
So Steve, back at your method. You first draw the front of the cube as the bigger square, and then the back of the cube as a smaller square, right? And then you have all those lines connected to each other, right?
Yes.
So it's almost the same idea as this one. The outer bigger cube is almost something like it's closer to the viewer in the W direction. That is the fourth direction in this case. That's the new direction in this case. This outer cube
What does-
is like closer along the fourth direction, and then this smaller cube is like further away from the observer along the fourth direction. And then what you will do is you will connect all the lines to all the corners. This is what it does over here. This one, that one, this one, that one, and then 4 back over here as well. But as the penalty of projection, as you can see, these newly connected lines are not perpendicular to the cubes anymore. But at least we know, in theory, that these lines should be perpendicular. Right?
Yes.
Okay,
What does
so-
the W mean? With?
So W, okay, so for example, if you still
One bar.
remember, we have X, Y, and Z, right?
Mm-hmm. Yeah.
When we attach a new axis, we call it W.
Oh,
It's like a
okay.
variable.
Well, not a variable, it's just a name. Projection, there are many ways to do it. So,
Oh.
for example, that your idea is what I would call parallel projection, because you just parallelly just push the square in a slightly newer direction on your paper, but of course not perpendicular, because a piece of paper only have 2 dimensions.
Dimensions.
So another way to do it is point projection. So in this case, Kappa, you have the light bulb, and then Steve, you have that cube, right?
Oh yeah.
So what in this case is, when you pick up the bulb and you click it, you press it, it will start shining light, right? Yep,
Aw.
I think you have it.
Hey.
So now-
it's almost
so
as bright as you.
So,
Thank
so Steve, what you can do is you can try to put the square at the middle just to make it float or whatsoever. And then Kappa, what you can do is you can try to put the light bulb above this cube. Now, because me personally, I'm on quest, I cannot see the shadow, but I believe the both of you can see there is a shadow on the floor, right?
Look, Kappa! Look at the shadow! It's a square!
So as you can see, we have projected a 3D cube onto our 2D floor, right? So it's almost the same
look at
thing,
the
you see?
lines.
So as you can
Above
see,
the-
this upper square is getting projected at the outsider. You know, and then the lower square is getting
Yo.
projected as the smaller square, right? As we can see that as 3-dimensional creatures, we can see all of these edges are all perpendicular to itself. We all know that. But if any little ant on this carpet see this shadow, they will say, hey, there are some other extra lines which are not perpendicular. But actually we know there are. This is a penalty of projection. So we have that.
We lose. Oh yeah, I can see it.
That's
That's way better when
sick.
you rotate it, so you can actually see.
Yep.
Dude, I
And then
love
another fun
4D.
stuff is when you okay, this little toy over here, when
Oh
you
my God,
grab
that
the
looks
cube and you click it, it becomes something else.
This?
Yes.
Polyhedron. I don't know.
No, this is a
This-
poly high from
This is an icosahedron, 20 spaces, normally known as a D20. So,
D20
one thing
Jesus.
you can also see this
D20.
is, but if you were to put a light source at the north pole of this sphere over here, this is also known as stereographic projection. So in this case, this is also one way in order to map the whole globe onto a 2D flat plane.
Oh,
So as you can
you
see,
that? Cap,
the North Pole and the South Pole will get projected
look at
onto the plane as well. Now, because, you know, projection,
Sick.
distortion is under avoidable. So we have that.
Yeah, it's unfortunate.
Dude. Dude, this is pretty freaking sick. I have a whole new appreciation for the 4D homies.
Just in case we're
We
not
don't
done
know.
yet. So just in case, let me sit down. Yeah, there we go. Chill. There we go. Okay, so one interesting question to think when it comes to like 4D or whatsoever or topic like this is, okay, what will happen or what will we see as 3D creatures when a 4D sphere passes through our environment? Do you have any like imaginations or guesses?
Depth.
That, I need more than that. Kappa,
Like,
you got
what-
any idea? What would it be like?
If it's a 3D space and you're a 4D sphere, what even is a 4D sphere?
So a 4D sphere, you can think of it this way. If you still remember, we have the coordinate. Oh wait, I can grab this coordinate thingy. Oh boy, someone sink the coordinate into the couch. Oh no.
Here you go.
There we go. Thank you. Okay, so if you still let's start from the most simplest sphere we can ever make.
Mm-hmm.
So the simplest sphere that we can make is, let's just say we didn't call it a sphere, we call it a circle. So any point on this plane over here which has a length or have a distance of some certain of radius away from the origin, that counts as a part of the circle. So in this case, we can know this circle right here is a perfect circle that we need that have a radius of 1, right? So now let's just say, all right, how about let's go into the new dimension. Let's add a new dimension. So in this case,
A new plane.
so in this case, the dot or the point can be any elsewhere in this 3D environment as long as the distance from it to the origin point is a fixed radius. So that is now a sphere, right? Okay, so a 4D sphere, it would be something like, all right, we have X, Y, and Z, and then a new dimension, W. Well, I cannot show it here because we are all 3D creatures. As long as this point, also along in the W direction, has a length in between the origin point is a fixed radius, then that is also a part of the 4D sphere. So one thing you can imagine what's a 4D sphere is, it's a whole bunch of 3D spheres got stacked together and then compact along the 4th direction. So most of the time people struggle to like understand what is going on. So that's why I have another toy. Where's the flat scanner? Oh, there we go. So if I remember correctly, we have this. And just in case, can one of you grab one of the colorful ball back there?
Sir?
There we go. Thanks. So this is what I would call force section. So instead of like thinking what is a 4D sphere passing through a 3D environment like, we can go one dimension lower. Okay, there we go. I lagged a little bit.
You're fine.
So in this case, this is a little toy that I made. So one of you can give it a go or whatsoever. Yeah.
You have the honors.
Whoa. Okay. So, one of you want to give it a try and grab the ball?
You got that.
You want me to get it?
Let him. Yeah.
Oh,
I got you.
Oh, you got it? Okay, cool.
Alright,
So,
yeah, I got the ball.
so in this case, I will. In
I
this
want to see
case,
from a better angle.
you can come over here. You can come over here instead, or you can go in front or whatsoever. Yeah, here also works. So, as this is a cross-section scanner, in this case, as you can see, when the ball passes through, you can see the cross-section on the right-hand side of the screen. What to us is right, on the on the other side is left.
Oh my gosh.
So as you can see, when Thief is passing through the ball, not your head,
face.
not now. So as you can see, when
Sorry.
Thief passes through the ball, we can see this ball over here is a three-dimensional object, but on the screen, it's just a whole bunch of circles, right?
Mm-hmm. Different,
So
varying in
so
different sizes.
yes. So if Thief passes the ball slowly, we can see it starts from a vertices, like a dot in the middle, and then
Yes.
if it slowly continues, the circle will grow, right?
This
And
reminds me
it
of
will keep on growing. Hmm?
of 3D printing when I need to extrude the
Almost
layers.
something like that. Yes. Yes.
It shows it to me like this, and that's how I see it actually print out layer
Mm,
by layer
Yep.
by
yes.
layer.
So as you can see, when it
Oh,
so when it passed through like the equator or somewhere around, the circle will reach its maximum radius, right?
Mm-hmm.
Well, the camera cannot see you from there, but okay.
You can see his
oh
hands.
sorry, camera.
And then once the ball passes through this 2D flat plane, the circle will collapse, and then it will become a single point. Just in case you're not grabbing the ball, but
Oh yeah, sorry.
so as you can see, it
So-
starts to collapse down back to a point. And then when it leaves the plane, it disappears. Right?
Look how small that point is.
Alright, your turn.
So
Put
now,
it through
so
second
now
seat.
we can go back to the original question. What does it look like when a 4D sphere passes through our 3D environment? So, like now we can imagine, like let's say this is our 4D sphere, and then this plane is our living area, yeah, or whatsoever, right? So if everything goes one dimension higher, right? A circle goes one dimension higher, what would that be?
Another
Higher?
circle on
So-
top of it.
So you see, so if this is a 4D sphere, right?
Yes.
Okay, so one thing, let's go back to the normal sense whatsoever. Let's just treat this as a 3D sphere for now. So
Okay.
at least we know every time when we take a cross section of it, right? 3 dimension goes to 2 dimension, right? So every time when you take a slice of something, the shape, the cross section, the slice you will have is always 1 dimension lower, right? This means that if you take a cross section and then you upgrade it, this means the new upgraded thing will be 1 dimension higher, right?
Uh-huh.
So in our normal sense, you take the cross section. Oh wait, let me get rid of my phone alarm.
Oh no.
Wake up, Razor. Wake
There
up.
we go. Wood. Oh, there we go. Thanks. There we go.
There you go.
What would happen if I?
I should have. Uh-oh.
Maybe like after the video, huh?
Look at this stare. It's giving
I
you
feel
that
bad. I'm
medicine.
not gonna do it. I'm not gonna do. I know you're not there, but I'm not gonna do it. I promise.
Oh my goodness. Oh my god, can we do the bee?
Yeah, do the bee. I want to see. I just want to start grabbing random stuff.
I know. No. No.
What?
It doesn't go through.
Oh boy, very.
With the light.
No. Razor, I know you're there. Look at the. Oh damn! The light even emits a light from the light. That is crazy.
Dude, this is confusing, but like I'm sort of getting it.
Yeah, me too.
Especially like with this. Now that I understand, like, we see, like, when you mentioned a 3D printer, it's like, holy moly.
Does your arm go through it? Let me see. Oh yeah, your hand does go through it. I can
It's
see
your
your
face. Go
clothes
do
in
your
your arm.
face.
You do your face. I already did mine.
I don't. Did it...
Hey, it works. It works. Yeah, it doesn't show it for you, but it shows it. Oh my god. Hold on, let me take a picture of it for you. Put your face in. Wait. I'll tell you when to stop. Keep going. A little bit more. A
I
little
feel
bit
like
more.
you're gonna see a little bit more.
Oh. Oh, oh my god.
Please, you better
No,
not.
I didn't. No, wait. I'll send it to you right now. I'll prove it to you. I just realized what you meant. No, Cap. I don't want to see your booba.
Shut up.
Are you having fun?
It's definitely interesting. I'm learning. Learning, but I'm also confused. But it's like, I'm learning at the same time. It's like, E.
It looks so ugly.
Oh my god.
That's so good. Oh yeah, dude.
Well, it's different because, you know, this is not an actual 3D model. I'm missing my, like, the top of my head, but as close as you can get.
Oh,
Where did Razor go?
he
Oh,
crashed.
there's next. Ah, we were almost done.
Okay.
Very unfortunate.
I can't see myself.
Put your leg through it. Oh my god! Wait, move back a little bit. Wait, go back. Right there. Go, go.
I do, boy. Wait, I have an idea. Hold up, he wants to join me. Oh man, I don't have a butt. That's tough.
No,
dude.
I think the inside of your body is like shrunken.
Yeah.
I don't know if... Is that what I...
All I saw was ribs. Get you went. Why is this such a good photo? Get out of here.
Oh, my phone went off. Hold on, I kind of want to light up the cube again. Like, we could probably project it on this wall. Look,
That's a cube.
fourth dimension.
Damn, bro.
It's,
And then
it reminds me of
only
like...
when you get
Uh-huh.
close enough, it makes it into that weird square. This one turns it into this one. Yeah, see?
Well, if you think it that way, and my brain, I'm like thinking of it of like
But-
another there's space projected onto the wall. Like it's basically this cube, but onto the wall. And we are the light, and we're looking in it.
Oh.
In a sense.
Oh.
Yeah, that's what I'm
You see
thinking.
the different angles?
Yeah. So
Oh,
we're currently
welcome back.
seeing on this plane.
So just in case, where did you put the metal plate? Because it's gone for me.
It's still here.
Yeah, it's right here.
Oh, okay, there we go. Okay. So, okay, there we go. So if we get back to the question, it would be something like, so now since we already know that every time when we take a cross section, it will go one dimensional lower, and then if we take our cross section and then upgrade it, we are able to go one dimension higher, right?
Mm-hmm.
So let's say if a 4D sphere is passing through our 3D environment, what is the slice of a 4D sphere?
A circle.
Remember that we go one dimension higher. So a 4D sphere, what is a slice of 4D sphere? Every time we take a slice of it, it goes one dimension lower. A 4D sphere, 4D goes lower, what it becomes?
It's a 3D.
Yes, so a 3D sphere is just a normal sphere, right?
Mm-hmm.
So a 4D sphere passes through our room or whatsoever. Over there, okay, we see a circle whatsoever, but in theory, if a 4D sphere were to pass through our world, we would see it as a normal 3D sphere, right?
We're incapable of seeing it as a 4D.
Yes, so at the beginning, we will start from a little point, like a little tiny ball. And then this ball will grow, expand, until some certain point, that is its maximum radius. And then this ball will shrink. And then it becomes a point, and it disappears. So that's what a 4D sphere will look like. Like, imagine like, a real 4D sphere just appears, we will just see a small ball grows big, expand, and then stop, and then start shrinking, and then back to a point, gone.
And then just disappear from our plane.
Yes, because we cannot see it. So we have that.
Oh, interesting.
Yep. So in this case, many people have talked about different 4D objects or whatsoever. So we can talk a few of them. Like,
It's a Klein
where's the
bottle.
Tesseract? Where's the Tesseract?
It's
Over here.
It's a bomb.
Where's the 4D sphere? There we go. So just in case, because we are 3D living beings, we have to like project those 4D objects onto our 3D environment. So just like this one, we have this Tesseract, which is just a simple 3D cube getting pushed along the fourth direction and then done. But we have to project it, and then we have distortion. So now we have this. So this is sometimes also known as the shadow of a 4D cube. Just like how we use the light bulb and then we shine our normal 3D cube onto the floor. It's almost something like that as well. Now this one over here is a Klein bottle. So as you can see, the reason why this thing is fourth dimension is because we can see this, we have a small part that passes through itself, but actually not quite. What's happening over here is this little tube over here connects into the fourth dimension, and then the fourth dimension do not have this cone, so it is able to quote unquote pass through it and then coming back from the fourth dimension and then get connected over here and then continue.
I've
So,
seen
you
variations
see?
of a Klein bottle.
Yeah, I've seen that too.
Yeah, sometimes online or whatsoever, if you watch YouTube or whatsoever, probably all of you have heard of what, like 5D chess, 4D chess, whatsoever, right?
Yes.
It's almost the same idea. In this case, they go from 1D, which is just a single line, and then they'll go for 2D, which is our normal chess, right? And then now they have multiple copies, and then they stack on top of it, and now it's a 3-dimensional chess, right? And
Like
you
a
take
3
this
by 3.
whole thing, you copy it multiple times, and that's your 4D chess. So it's almost the same thing over here. Almost the same thing over here. Like, you can imagine, like, this tube over here goes along all the way. In order to pass through this wall, it has to go into the 4th dimension. And then in that 4th dimension, you walk past through it, and then you come back over here. Now you're inside the tube, or inside the bottle, and then you continue your journey. So we have that.
So I feel like putting anything through a solid object, would that mean you're passing through the 4th dimension?
It depends. If things are not allowed to pass through each other, then going into the 4th dimension and then coming back is the only way to quote-unquote pass through. However, if things are allowed to like pass through just like what you did, then no problem, no need to go all of that.
We're gonna pass the 4th dimension.
And technically speaking, we can actually go even higher though.
I
We're
Because
gonna
never
get
imagined.
even high.
Because in string theory, there are 11 dimensions.
Collect all the dimensions.
So we have that.
11 circles. Squares.
Well, it's not just that. So just in case, we can start wrapping things up. So quickly going through a dimension, you use that to like describe some kind of state or a trait or something like that. The more dimensions you have, the more numbers you need in order to describe that. Now, for a spatial dimension, every spatial dimension needs to be perpendicular to each other. And then if you take any object, right? You take the cross section of it, that cross section will be 1 dimension lower, right? And then of course we have so far a lot of ways to like project things. One of them is point projection, which is the one with the bulb, right?
I like that
And
one.
then if you put the bulb at the north pole of a sphere or whatsoever, or whatever 3D shape you have, that is called a stereographic projection. Another projection is the classical cube drawing piece on a piece of paper projection. I call it the orthographic projection. So in that case, on your normal plane, all the lines which are in the same dimension or direction will be parallel on that line, but different dimensions will be projected in a skewed way. Like they're not perpendicular anymore, but deep in our mind we know that it is still perpendicular. It's just not on that flat plane. So we have that.
See? Awesome.
Alright, so guys, if you watch this thing to the very end, thanks for watching, and then we see you in the next video. Bye.
Bye. Tune in next
Let me
week.
turn off my phone.
Tune in next
is
week when
going
we
on?
apply 4D physics to get goth babes.
Oh no.
here.
I will need to censor that out.
Hey, baby. You ever see what
Stop.
the 4th dimension is? Okay.
Oh no.
You ever cross an object through a plane?
Oh my goodness.
I wouldn't mind crossing with you. It worked.
No, I
Oh,
just get
Pebble's gonna
laughed.
kill me. Pebble's gonna kill me.
Okay.
Klein bar,
It's
not the Klein bar. Bottle. It's confusing.
Oh, that's what you. Okay.
He's got an idea. Like,
Oh, come on.